All right, 5 more seconds. All right, I'm going to close this question in 5, 4, 3, 2, and 1. Okay. Now, I know when I reveal your responses, I'm going to see that you have clicked on all of them. I'm going to say, there you go. Okay. Okay. Anyway, so however, only some of these ionic compounds, 50% of you recognize them. But here are these ionic compounds. Okay. I separated them for you. Now, what I want you to do is, I want you to come up with a criteria that we can use to distinguish between ionic compounds versus molecular compounds. Okay. I'll let you do this on top pad. You use the word metal. Right? Ionic means metal and non-metal, metals, non-metals, metals are for ionic. Okay, so it has something to do with the metals. Okay, anyway, good. So the criteria that we can use to distinguish between ionic versus molecular is if your compound contains a metallic element. Let me go back to the table. Okay, so if your compound contains a metallic element like, say, sodium or titanium or magnesium or copper, okay, so chances are you are dealing with an ionic compound. On the other hand, if you look at the molecular compounds, they are only made of non-metallic elements. Now, here's the thing. I know that some of us need a refresher on how to identify metallic versus non-metallic elements. Now, the good thing is it's really, really easy. So what we want to do is we want to have a table called periodic table. Maybe you have heard of that, right? Looks something like this. So in the periodic table, there's only a handful of non-metallic elements, which are restricted to the top right corner of the periodic table. Okay. Most of the other elements are metallic elements. You can count the non-metallic elements with your fingers, maybe a couple of toes. Okay. So, but most of the other elements are metallic elements. Okay. So, for examples for non-metallic elements are like carbon, nitrogen, oxygen, fluorine, sulfur, phosphorus. So, this is only a few of them, but most of the others are metallic elements. There are some other elements that are in between metal and non-metal, we know depending on what they are combining with, but we are not going to be dealing with them anyway. All right. Any questions, concerns, comments at this moment? Anything? So one more time, if your compound contains a metallic element combined with a non-metallic element, okay, that's going to be an ionic compound. It is not a technically most correct definition of ionic compounds, but we will come up with the definition as well. Not that I'm going to be asking for definitions in an exam, but we'll talk about them in a minute, okay? Any questions, concerns, comments at this moment? Okay. So let's think about the ionic bond for a second, okay? So before we do the ionic bond, let's think about a normal covalent bond, like, a non-polar covalent bond like F2, okay? So electrons are equally distributed between the two atoms there. It's going to be a non-polar bond. But if you have electronegativity difference between the two atoms, then the more electronegative atom will have a partial negative charge. Why? The electrons will spend more time around the more electronegative atom. And then greater the electronegativity difference, more pronounced this partial charge separation is. That's what happens when you go from HBr to HF. The electronegativity difference is going to be more pronounced. It's going to be greater. Therefore, the partial charge separation is more pronounced. But when it comes to the ionic compounds, so the ionic bond, its electronegativity difference is so much, it's like transferring electrons from the less electronegative atom to the more electronegative atom. As a result of that, the more electronegative atom is going to get an actual charge, not a partial charge anymore, an actual charge, actual negative charge, while the less electronegative atom is going to be losing electrons. As a result of that, they're going to get an actual positive charge. Okay? So once you get the actual charges, negative and positive charges, we give them names as well. Does anybody know what we call the positively charged atom? Yeah, it's called the cation. And the negatively charged ion? Anion. Okay. So ionic compounds are made with cations and anions, that's going to be the formal definition for ionic compound. Okay? So ionic compounds are made of cations and anions. That's the formal definition. And cations are the positively charged ions, and anions are the negatively charged ions. That's it. All right. Any questions, concerns, comments at this point? Now, as of now, we should be able to identify ionic compounds and distinguish ionic compounds from the covalent compounds. Okay, so at this moment, and then we know what is meant by a cation and what is meant by an anion. That's it. That's all we have learned so far. Okay. So, any questions, concerns, comments before we do something else with this? Okay. Now that we know what ionic compounds are, what I want you to do is, I want you to draw me pictures. Okay? So I want you to draw a sub-microscopic representation of a covalent compound and ionic compound. You know what? I'll do the covalent compound. You do the ionic compound, okay? So if somebody asks me to draw a particulate level representation or particle representation of a covalent compound, I would do this. Okay? So let's say that I'm going to draw carbon monoxide, which is a covalent compound. So I'm going to have carbon atoms and oxygen atoms, right? So it's going to be something like this. I'm going to draw a particle representation like this. Okay? Here's a particle representation, a particular level representation of a covalent compound, carbon monoxide. Okay, your turn. Draw me a submicroscopic or particle representation of an ionic compound. Let's take magnesium oxide. Magnesium is the metal. Oxygen is the non-metal. Okay. Can you draw me the submicroscopic representation of magnesium oxide for me? Go ahead. Okay. So if I drew magnesium oxide, first of all, this is one of the main differences between molecular and ionic compounds. Ionic compounds look really different at a particular level. Okay. So when it comes to ionic compounds, we do not have molecules, right? So magnesium oxide has cations and anions. So each cation is surrounded by anions, and anions are surrounded by cations. Okay, that's what we have in an ionic compound. Okay, we call this an ionic lattice or a network of ions. Okay, now one more time. So in ionic compounds, we do not have molecules. That's one of the main things that we need to understand. Okay, no molecules in ionic compounds. We cannot call them molecules. What we have is a lattice or a network of ions, which we call as an ionic lattice. It's like a brick wall. Okay, every cation is surrounded by the anions, and the anions are surrounded by the cations. That's what we have in ionic compounds. Okay. What questions, concerns, comments do we have at this moment? Anything? Any questions, concerns, comments? Okay. That this is one of the main differences I want you to know about the ionic compounds versus molecular compounds. Okay. In molecular compounds, we have molecules. In ionic compounds, we don't have molecules. We have a network of ions. That's it. Okay. Any questions at this moment? Anything? Okay, so we know how ionic compounds look like at a particular level now. With that, let's do this. Now, I want to go back one more time. Bear with me for a second. Right. Now, here's the thing though. So even though we do not have molecules in ionic compounds, we still write the chemical formula, right? For example, so for magnesium oxide, we write MgO. Okay. If we do not have molecules of magnesium oxide, what does this represent? Okay, so I'll do another example. Here's sodium chloride. Does anybody know what sodium chloride is? That's table salt, right? Okay, so when you write the chemical formula of table salt, you write NaCl. Now we know now that NaCl does not have molecules. So when we write the chemical formula, it is not a molecular formula anymore. Okay, what does it represent? I'll give you 30 seconds. What does the chemical formula of an ionic compound represent then? What is it? What does it tell you, in other words? What does the chemical formula of an ionic compound represent? What does it tell you? Those are not molecules. They're not molecules. What is it?
Get this made enough.
Anybody? I have a hand over there. Russell. Thank you, Anaya. Russell, again, the question is, what do we write when we write the chemical formula of ionic compound?
It's the ratio of the two atoms.
Thank you. The ratio between the ions. That's it. Okay. So when we write the chemical formula, so for example, in sodium chloride, what we have written here is sodium 1 and chlorine 1. This 1 is implied, meaning the ratio between the sodium ions and the chloride ions is 1 to 1. The ratio between the cations and the anions is 1 to 1. And that is what we're writing as the chemical formula of ionic compounds. This is same as the empirical formula. The lowest whole number ratio between the atoms or the ions. Okay, not the atoms, let's call the ions. Okay, that is what is represented by the chemical formula. All right, any questions at this point? Now, one other thing, okay? Now, why is it 1 to 1? Does anybody know? In sodium chloride, why is it 1 to 1? Why isn't it like NaCl2 or I don't know, something else? Anybody? Lila, do you know? Why is it 1 to 1, Lila? Why isn't it 1 to 2 or 2 to 1 or 1 to 3? So that part is already done, right? Because we know sodium is going to be less electronegative, chlorine is more electronegative, the other electron has been transferred already. Sodium has a positive charge, chlorine has a negative charge. That part is already done. Now the question is, why is the ratio 1 to 1? Eden, do you want to have a stab at it? I saw your hand. I'll come back to you, Lila, okay?
Chlorine's favorite show.
Okay. Can we simplify it a little bit more though? Leo, you want to simplify it a little bit more? I mean, Eden is on the right track. I think
So is it that one is a +1 charge, the other one's a -1 charge? 1 over 1?
why 1 over 1? Why can't it be 1 over 2?
Because it's 1.
No, I know. Yeah, you got it. The reason, okay, one more time. Let me rephrase what you're trying to say, Leo. Okay, so sodium is +1, chlorine is -1. To have a neutral compound, we just need one of each, right? If you have, say, 1 to 2, then it's not going to be neutral anymore, right? So if you have 1 sodium and 2 chlorides, then that will be a net charge of -1. That's a no-go. Okay. The goal is to have a neutral compound, charge neutrality. To neutralize 1 sodium, we just need 1 chloride. That's why the ratio is 1 to 1. Okay. Similarly, we saw magnesium oxide before, right? So when we wrote magnesium oxide, okay, magnesium is going to form 2+. We'll learn how to determine that. And you know what? You do it. I'm sorry. You should do it. I should do it. Okay. Now, let's determine the charges of this. Here we go. Here are the 4 electron spectra of magnesium and oxygen. Can you let me know the charges of each of these atoms? in an ionic compound based on the 4-electron spectrum? Go ahead. I'm going to close this question in 5, 4, 3, 2, and 1. Okay. And here are our responses. Okay. All right. Now, the most popular answers are the correct answers as well. Can somebody tell me why though? Why does magnesium form 2 plus? Why not 1 plus? Why not 3 plus? Why is it 2 plus? Anybody? Thank you, Isaac. Thank you. Can I have the mic? Isaac, why does magnesium form 2 plus? Based on, okay, go for it.
Yeah, so I think it's because magnesium has 2 electrons in its
Just electrons.
valence
Let me point it
shell,
out.
yeah.
Isaac, give me 1 second. Okay. So Isaac is pointing out that magnesium has 2 valence electrons. Okay.
Yeah, and so since it has only 2, it's difficult to get up to 8 to fill it. So it's more willing to give it away, give those 2 electrons away and form a net positive charge.
Okay. So are you telling me that they want to be like noble?
Yes.
Yeah. Okay. Okay. So your point is they want to be like noble gases. It is easier for it to lose 2 to become like neon rather than gaining 6 more to become like argon.
Yes.
That's absolutely correct. Yeah. So that's what we're looking for. So they are trying to become like noble gases. Okay. So for magnesium to become noble, it can either lose 2 or gain 6. What is easier? Losing 2 is easier. That's why magnesium is going to lose 2 electrons and become 2 plus. What about oxygen? What's the name? Say one more time. Kaden, why is oxygen forming -2? So let's keep the microphone, Kaden. Okay. So how many valence electrons does it have?
4.
Oxygen.
Oh, yeah, 6.
Yes, 6. Right. So if oxygen to become like a noble gas, it has 2 options, right? It can either gain 2 or lose 6. What is more likely?
Gain 2.
Gaining 2 is more likely. If it gains 2 electrons, 2 negative charges, what will be the charge of oxygen then?
-2.
-2. That's why it's going to form -2. That's it. Yeah, that's all we need to consider there. Yeah, wonderful. Thank you. All right. So one more time, the Holy Grail is to become noble. They all want to become noble. Okay. So how they become noble? I mean, how can they achieve that? The easiest way, that's what they're going to follow. Okay. So anyway, now you see that if we know the number of valence electrons, this is 6, this is 2. Okay. If we know the number of valence electrons, we can predict what charge they are going to form in an ionic compound. Yeah. Is there a way to know the number of valence electrons of any element? How can we know the number of valence electrons of any element? What can we use? Thank you. A periodic table, right? If you go to a periodic table, let me show you one. Okay. So the periodic table tells you. Let me go here. Okay. So here's a periodic table. Okay. It tells you the valence electrons in any element, right? For example, so do you see that for the first group here, first column of the first group, you see 1A. Oh, no, I need a different color. I need a nice color. Okay. You see 1A here? What does this 1 represent? Does anybody know? That 1 represents what? In 1A, the group 1A, that 1 represents what? Come that again, miss. Thank you. 1 valence electron. It tells you the number of valence electrons. Go to the next group, the second group. Okay. Guess what? You have 2 there. You see 2? See 2? Meaning it has 2 valence electrons. Let's go to the other side. These are noble gases. You have 8. Okay, this is Roman, and then you have Arabic as well. This 8 tells us the valence, it has 8 valence electrons. Okay. So what about this group here? How many valence electrons do they have? 7 valence electrons. How do we know? You have number 7 in front of A. Okay. So we can ignore these transition metals. They are B. Okay. So we don't worry about the Bs. So focus on the A groups only and answer this question. Go ahead. I'll give you a minute. Responses. Okay. For some reason, 7A and 6A is a little bit lower than 1 and 2A. Okay. So most of us said 1A and 2A produces +1 and +2 respectively. Okay, why? 1A means they have, it's not relevant to hydrogen, by the way. Okay. So if you look at the rest of the 1A elements, they have 1 electron in the valence shell. Therefore, them to become like a noble gas, it's easier for them to remove 1 electron. Therefore, they're going to form +1 charges. Okay. Move on over. Group 2 has 2 valence electrons. Therefore, they're going to lose 2 electrons to become like a noble gas rather than gaining 6. And group 3, the same way. Okay. They have 3 valence electrons. They are going to lose 3 electrons to become noble rather than gaining 5. Okay. So this should be +1, +2, and +3. Now we go to the other side. Let's switch colors. Okay. Group 7 has 7 valence electrons. For them to become like a noble gas, it is easier for them to gain 1 electron rather than losing 7. If it gains electron, it's going to have a negative charge, -1. Move on over oxygen, sulfur. Okay, they have 6 to become like noble gas. They're going to gain 2 electrons. They have a -2. Nitrogen, phosphorus is going to gain 3 electrons. Okay, -3. Carbon is going to gain 4 electrons, therefore -4. So they should be the charges formed by each of these groups. All right. What questions, concerns, comments do we have? Anything? Any questions, concerns, comments at this point? Now the point is this. If we want to know the charge of an element in an ionic compound, all we need is a periodic table. You go there, go to their group, and determine how many valence electrons it has, and based on that, we should be able to determine the charge of that element in an ionic compound. Yes? Yeah? Any questions at this point? Anything? Remember names one more time. Everybody has a question, right?
Why is carbon a -4?
All right. The question is, why is carbon -4, not positive 4? The reason is carbon is a non-metallic element. Non-metallic elements are forming negative charges, not positive charge. Yeah, that's why carbon is going to form -4. Yeah. Any other questions, concerns, comments? Okay. Now here's the thing, though. I said any element, okay, and you believed me. Okay. What about these guys? Any elements include these transition metals too, right? I conveniently skipped them, and then you were okay with it, right? What about these guys? Now, here's the thing. When it comes to transition metals, the ions they can produce, the charges they can produce in an ionic compound is, I don't know, I don't know the correct word for this. It's redunculous. Okay, I'm serious. Okay, I'll show you. So let's think about the transition metal manganese. Manganese can form +7, +6, +5, +4, +3, +2, and something like iron can form +6, +5, +4, +3, +2. So it can form many different ions. So just by considering the position in the periodic table, we cannot determine what charge they are going to form in an ionic compound. For that reason, whenever I give you a question about a transition metal, I'm going to give you more information. For an example, if I give you copper, okay, within parentheses, I'm going to write a number like this. If I write 1, what's the charge of copper there? Okay, you have to say +2. It's +1. Why? These are metals. Metals are always going to form positive charges or cations, okay? Therefore, if you have 1, that means it is going to be a +1 ion. If I have 2, that means +2. Nickel 1 means what then? Yeah, nickel 1 means, yeah, +1, right? Because you have 1 within the parentheses, that's it. So I'm going to give you some more information to determine the charges of these elements. All right. Now, at this moment, we know the difference between ionic and covalent compounds, and we know what is meant by the chemical formula of an ionic compound, and then we know how they look like at a particular level, and we know how to determine the charge of an element in an ionic compound using the periodic table. Okay, that's what we have done so far. Now, let's make sure that we really understand the chemical formula of ionic compounds. One more time. The Holy Grail is charge neutrality. We want to have a neutral compound. So let's pay attention to this for a second, okay? Let's think about combining sodium with chlorine gas, sodium solid with chlorine gas. By the way, sodium solid is a highly reactive metal. If you put this in water, it's going to explode, right? And there are YouTube videos on that. I mean, you should check them out. Okay, I mean, the water in your saliva is enough for it to explode. So if you put it in your mouth, it's going to explode in your mouth. All right, so don't do that. And chlorine gas is a highly toxic gas that was used as a chemical weapon in World War, I believe it's one, or maybe two. I think it's one. Anyway, okay, it's really toxic. Now, you take sodium solid and combine that with chlorine gas. What do we get? Anybody? What do we get when we combine sodium solid with chlorine gas? Salt, table salts, NaCl, right? What do you do with that? You sprinkle them on your French fries and eat them. Yeah? That's how ionic is, these are. Not ironic, is, you know. Anyway, so the idea is this. From the sodium solid, we are going to get sodium atoms. With chlorine gas, I'm going to get chlorine atoms. And sodium is in group 1, therefore it's going to form +1 ions. And chlorine is in group 7, therefore it's going to form -1 ions. Therefore, when they combine to have a neutral compound, you need to have, for each sodium, we need to have 1 chloride. We just need 1 chloride ion to neutralize 1 sodium. Therefore, the chemical formula is NaCl. Let's do another one, okay? Let's think about magnesium. Solid combining with Cl2 gas. One more time, just for the illustration here, okay? From the magnesium solid, we're going to get magnesium atoms. From chlorine gas, once again, we are going to get Cl atoms. So that's all I care about. I don't care about the subscript over here, right? I just get chlorine atoms. Okay, magnesium. What is the charge of magnesium in an ionic compound? 2+, thank you. Why? It is in group 2. Therefore, it's going to remove those 2 electrons to become noble. Therefore, it's going to form 2+ ions. And chlorine is going to form -1. Therefore, to neutralize 1 magnesium ion, how many chloride ions do we need? 2. Therefore, when you write the chemical formula, you write Mg, Cl. The ratio is 1 to 2. This 1 is implied. Therefore, you don't have to write 1. What I want to erase. Okay, so you're going to just write MgCl2. All right, let's do one more. Let's combine aluminum. Oh, aluminium. Which one is it? Is it aluminum? Aluminum? Aluminium. All right, so let's combine aluminium solid with oxygen gas. What do we get? Go ahead. This is before. So, one more time. The idea is to have a neutral compound. The charge should add up to 0, right? So, it turns out if you use the charge of the cation as the subscript of the anion, and charge of the anion, which is 1, is implied over here, as the subscript of the cation, you're going to get the charges balanced out, without thinking too much. So let's see if that works for this as well. So we have aluminum or aluminium, whatever you call it. One more time. What do you call it again? Okay. All right, aluminum. All right. So from aluminum solid, we're going to get aluminum atoms. From oxygen gas, we're going to get oxygen atoms. Okay. And aluminum is in group what? Which group? Which group is in aluminum in? Group 3, therefore it's going to form 3+ ions. Why? It's going to lose 3 electrons to become noble. and oxygen is in group 6, therefore it's going to gain 2 electrons to become -2. So in your compound, you have aluminum combined with oxygen. So I'm going to swap the charges now. Okay, I'm going to write the charge of the anion as the subscript of the cation, and charge of the cation as the subscript of the anion, and then I get the chemical formula of the ionic compound. Now let's check this out. Okay, we know aluminum is +3. You have 2 of them. 2 times +3 is +6 on the cation side, and oxygen is -2. 3 times -2 is -6. +6 plus -6 is 0. So we have a neutral ionic compound when you do that. All right. What questions, concerns, comments do we have? Yes, Laila.
Compounds where there's like more than two. How would you do that for ionic compounds that have like more than 2 atoms?
We'll work some of them later.
Okay.
So when you have more than 2 atoms, like you're talking about polyatomic ions, right?
Yeah.
You consider the charge of the entire ion, not just one atom. We'll do one of them later.
Okay.
Yeah. Yes. Yes. Remember your name, sir?
Adam.
Adam, go ahead.
Okay, so when bonding, like in this example, aluminum is a solid, oxygen is a gas. And when, like, after the bonding, do you also need to include the phase change? And then along with that, how do you know what the phase change is?
Having a reaction here yet, Adam. Okay. So if we combine these two, the only possibility for an ionic compound is Al2O3. That's all we are looking for.
Okay.
We're not worried about the phase of our product.
Okay, thank you.
All right. Any other questions, concerns, comments? Okay. All right. Let's do this. All right. By the way, so you can see when I write the chemical name, okay, I write sodium, the name of the cation, and name of the anion with the suffix "ide." So chlorine became chloride. Oxygen became oxide. Okay, so we add that suffix, the "ide" suffix, to the anion. That's something to keep in mind. All right. Now with that, can we try this? I recommend that you write the formulas yourself first and then check the options for the correct answers. And on your whiteboards, I want you to write the chemical formula names, like the chemical names. Went around, and then some people some of you started using the subscript over here, okay, like 8 to 9, okay, whatever, okay. So and then you realize it doesn't matter, which is good. Okay, that's the whole purpose of this activity. Now, again, what matters to us is from potassium solid, we're going to get potassium atoms. From fluorine gas, F2 gas, we're going to get fluorine atoms. I don't care about this subscript over here. It doesn't matter, right? All I care about is what atoms I get from fluorine gas or from F2 gas. I'm going to get F atoms, right? And potassium is in group 1, therefore it's going to form +1. And fluorine is group 7, therefore it's going to form -1. When they combine, it's going to be 1-to-1 ratio, therefore it should be Kf. And the name must be potassium fluoride. Okay. And then when it comes to calcium oxide, from calcium solid, we're going to get calcium atoms. From O2 gas, we're going to get oxygen atoms. Calcium is group 2, therefore it's going to form +2. Oxygen is group 6, therefore it's going to form -2 to become noble, gain 2 electrons to become noble. Okay. Therefore, to neutralize 1 calcium, you just need 1 oxide ion, O2. I'm sorry, O, right? O2 minus. Okay, so therefore the chemical formula is CaO. Calcium oxide is the name. All right, I'm going to do this one. Calcium again is calcium, should be 2+. And from N2, we're going to get nitrogen atoms. It's in the 5th group, therefore it's going to gain 3 electrons to become 3-. Okay, and then in our compound, we're going to have calcium and nitrogen. All I'm going to do is I'm going to swap the charges. I'm going to use the charge of the anion as the subscript for the cation and charge of the cation as the subscript for the anion, and this should be the chemical formula of calcium. What do you call that? What? How do we pronounce it? Calcium what? Calcium nitrogen? Nitride. Thank you. Calcium nitride. Okay. I'm gonna close this question now because I want to see how we did on the other one. Okay. So most of it selected calcium oxide, potassium fluoride, okay, and calcium nitride. Now, there's no correct answer for sodium sulfide. The reason is sodium is going to form +1. And from sulfur S8, we are going to get sulfur atoms. Sulfur is in group 6, therefore it's going to form -2. Therefore, to neutralize one sulfur, we're going to need 2 sodiums. Therefore, the chemical formula must be Na2S. But none of the options are Na2S. Therefore, we should not have picked C, right? C cannot be our answer. It has to be Na2S. Therefore, that answer is incorrect. Okay. Anyway, that's called sodium sulfide. All right. Any questions, concerns, comments at this point? Anything that I can clarify? Any questions, concerns, comments? Paul, are you doing okay? Yeah? Okay. Yeah, Laila, can I have the microphone with Laila, please? Laila, go ahead.
Like the word endings for the anon, when we say like the names of the like ionic compounds, like how do we figure out their names?
Oh, so the cation names remains the same. For example, sodium with sulfur, right? Sodium remains the same. For sulfur, you're going to add the "ide" suffix. It's going to be sodium sulfide, and then calcium oxide, calcium nitride, "ide." Yeah, Alexis.
Will we have to know how to identify the names of the compounds on the exams or quizzes?
It's a fair game. Yeah, it's just "ide."
Okay,
I mean, for the anion, that's all you need to know.
okay.
I don't think they will go after that, but we should be able to do that. Any other questions, concerns, comments? Okay. Now that we know, by the way, there are good discussion worksheet questions on this. I did about 6 of them last night with my 107B class. If you get a chance, go over them. All right, let's do one more question from the ionic compounds introduction and then go on to properties. Go ahead. All right, let's do this together, okay? Now, I'm going to eliminate 2 options right away. What are those? A and B, thank you. Okay, why did I do that? Why did I eliminate A and B right away? They're molecules, right? In ionic compounds, we don't have molecules. Therefore, those two options are out. Now, we know it's an aluminum fluoride is an ionic compound, okay? Based on the name, we have "ide," which is reserved for the anions, okay? So aluminum is in group 3, therefore it's going to form +3. Fluoride is -1. Therefore, to neutralize one aluminum 3+, we're going to need 3 fluoride ions. And this should be the chemical formula. The chemical formula tells us the ratio between the cation and the anions are 1:3. Now, therefore, I'm going to eliminate option D as well. Why? There, the ratio between the gray ions and the red ions is 1:1. For every 1 gray ion, we have 1 red ion, right? Therefore, that doesn't match. Therefore, the correct option must be option C. Now, you can see there, for every 1 gray ion, we have 3 red ions. Therefore, that matches with the ratio in our ionic compound. Therefore, the correct answer is option C. All right. What questions, concerns, comments do we have at this moment? Any questions, concerns, comments? All right. Now we can expect Something like that on last quiz on Friday. Right? I'll reopen this in case somebody wants to revise their answers, but pay attention to whether you are given an ionic versus a molecular compound. Okay. If it is ionic, then look at the ratio between the ions. That's it. That's all you have to do. All right. So with that, we are done with an introduction to ionic compounds. We learned what ionic compounds are, how to distinguish between ionic compounds and the molecular compounds. And we talked about the chemical formula of ionic compounds, and then how to determine the charges of any ion or any element in an ionic compound using the periodic table. And we wrote chemical formulas for ionic compounds as well. Okay. That's what we have done in the introduction part. Now let's have a preview of coming attractions when it comes to the properties. All right. Here's how it goes. Now, let's think about covalent compounds. If we want to think about properties like boiling point, melting point, density, viscosity of covalent compounds, what did we use to do that? What can we use to explain the properties of covalent compounds? IMFs, intermolecular forces. Okay. Now, when it comes to ionic compounds, we have a problem. We don't have molecules. Therefore, we don't have IMFs. So, what can we use to determine the properties of ionic compounds then, like melting points? Any idea? The attractions between the cations and the anions. The ionic, in other words, the ionic force. Okay, we don't have the intermolecular forces because we don't have molecules, but we have ions and we have forces between the ions, inter-ionic interactions, right? So we'll be using the ionic force to explain the properties of ionic compound. Now, before I get into that, I want to point out something. Okay, we have seen this table before. The covalent bonds are really, really strong compared to intermolecular forces. They can range from 200 to 1200 kilojoules per mole. They're pretty strong. Okay. While the intermolecular forces can only go up to 40 kilojoules per mole. We have seen this before, right? So, but when it comes to ionic compounds, the ionic force can range from 400 to 4000 kilojoules per mole. They are extremely strong compared to even covalent bonds. Some of the covalent bonds. Okay. As a result of that, okay, the melting temperatures we are talking about here are really, really high. I'll give you an example. What's the boiling point of water? 100 degrees Celsius, right? Does anybody know, not the boiling, but the melting temperature of sodium chloride, your table salt? Does anybody know? It's 800 centigrades. 800 degrees Celsius. Okay. Why? In sodium chloride, we are dealing with ionic forces, which are much, much, much stronger than intermolecular forces that determines the boiling, melting points of covalent compounds. That's why we have so high melting temperatures for ionic compounds. We don't even talk about the boiling temperatures for ionic compounds. Okay. So, any questions, concerns come in so far? All right, let's talk about the force. Okay, so it goes like this. I'm going to switch to my notebook for a second. Okay, so the ionic force, to model the ionic force between the ions, we are going to be using the Coulomb's law. Okay, don't write this, please. Please don't write this. I'm going to tell you why. So it goes like the force is equal to 1 over 4 pi vacuum permittivity times the charge of the cation times the charge of the anion divided by the distance between the ions squared. Don't write this. I made it, okay? Because we're not going to deal with this at all. Now, all we care about from this is the ionic force is directly proportional to the charge product. So the charge of the cation times the charge of the anion. We only care about the absolute value of that. And inversely proportional to the distance between the ions squared. Okay. You have to have this in your notes in a nice box. Okay. This you can forget. We need to appreciate that the ionic force is directly proportional to the charge product and inversely proportional to the distance between the ions squared. Okay. So now just to make sense of this is my cation and this is my anion. The distance between the ions is the distance from the center of the cation to the center of the anion. This is what is meant by R. Okay. And then Q sub plus is the cation charge. Q sub minus is the anion charge. Okay. And then the R is the distance between the ions. Please zoom in if I can. Okay. Now, at this point, we are already done with the cation charge and the anion charge. We know how to determine the charge of the cation and the anion of any element using the periodic table. Also, we know how to determine the distance between the ions as well, because that depends on the ion size. Because we have learned the periodic trends of the sizes or the size of the elements, right? Now, all we have to do is to remind us about these periodic trends, about the distance or the size of the sizes of the elements. Okay, 5, 4, 3, 2, and 1. And here our responses. Most of us said lithium plus is the smallest and potassium plus is the largest, and that's the correct answer as well. 90% of us are there. Okay. All right. Anyway, now why this is the trend? Now, lithium, sodium, potassium are in the same group. When you go down the group, what happens to the size? It gets bigger. Why? More shells. We're adding more shells. Okay. Each added shell is bigger than the previous one. That's why the size increases when you go down the group. What's going on there? See what we have next. Last question for today. This is just a preview, okay? So we'll remind us about like how to determine the size trends using the periodic table. And then when we come back on Thursday, we will play with this.
And the plus 2.
Okay? Actually, I like it. Okay? That's the correct answer as well. Okay? Most of you got it right. But you know what? Now, one more time. So sodium, magnesium, and aluminum are in the same, I believe they are in the same period, right? So sodium has 11 protons, magnesium has 12, aluminum has 13. The number of electrons wise, sodium plus has 10, magnesium 2 plus has 10, and aluminum 3 plus has 10 too, right? So they have the same number of electrons, but aluminum has the most number of protons. As a result of that, those 10 electrons are more strongly attracted to the nucleus of aluminum rather than magnesium and sodium. That's why aluminum 3 plus is the smallest, and then magnesium, and sodium is the largest. But we will revisit this when we come back on Thursday. And here's the attendance code. I'll see you Thursday.